right, good afternoon, everyone. This is going to be the classroom for transport phenomena for rest of the term. I have to remember how to write on chalkboard so they don't vibrate so much. So my name is Vivek. It's pronounced as we wake up in the morning. Just so you know. And your TA is Phil. So we'll be combining lectures with some recitations on Fridays, and every now and then when I will miss a lecture because of travel, I'll sometimes take over the recitation hour, which is Friday 2:30 to 4.
Yeah, that's what we're scheduled. If that time doesn't work for you, let me know. I'll send out an email with all the details associated with that, as well as like a poll for office hours and things like that. So we'll make sure it works for everyone.
So we'll be using Dean's analysis of transport phenomena. And just so that I know, how many of you have taken a transport phenomena class before? So there is a fair number who haven't. And so what we'll try to do is this week, Phil will hold a special lecture on vector and scalar calculus on Friday. And that's something we'll need going forward. But I didn't want to start with vector and scalar calculus here. So I'm going to go over certain concepts related to diffusion today. And then once we are done with some introductory material on vector and scalar calculus, we'll move on to more generalized treatment of all the transport phenomena. So that's GA. So we'll post the final office hours for both of us in time. And the main idea that we'll get across today is the idea of flux. And flux, or at least this idea, all is flux, is something that comes from a quote from a Greek philosopher. And that quote in Greek is pentarai, and that happens to be also what Society of Rheology uses. And the idea in transport phenomena in context of flux is that it's flow of mass, momentum, charge, or energy. So in transport phenomena, we are interested in describing flow of mass, momentum, charge, energy for solving problems like how much material diffuses into, say, a piece of wood when we place dye over it. Or when we move a ship in water, how much of the ship's momentum is transferred to water. Then if you have a charged species and we apply an electric field, how the charged species moves in response to electric field. This would be important in all kinds of electrochemical processes and will also play a role in biological processes. How momentum is transferred will be important in all kinds of fluid mechanics processes, and then because it controls how fast things flow, tells you how to determine how to calculate, say, velocity field when you apply a certain stress or force. This will allow you to also later calculate how motion of fluid brings in mass or energy or charge with it. And energy, of course, if you're going to live in Chicago, the only way you're going to survive is if you start to understand heat transfer and how to control temperature in your room and outside it, and how much is lost and how much is gained. And so all of those ideas of how much mass or momentum or charge or energy goes through an area per unit time is defined with this single concept, flux. And in next week, we'll write everything in terms of vectors and so on. But for now, you want to remember that this could be any quantity which specifies your mass or energy or charge or momentum per unit area per unit time. And these fluxes, which then involve transport of any of these quantities, always arise in response to spatial gradients or spatial variations of any of these quantities. So we call these non-equilibrium processes. So if I think about thermodynamics, in thermodynamics, you must have, at least some of you must have gone through a definition of equilibrium. And the equilibrium can be chemical, in which case chemical potential is matched. And when chemical potential is matched, there is no mass transfer. So that's the idea. As soon as you, say, place a dye or an ink in a container, you have a high concentration of ink at the center, and everywhere else there's a low concentration. So you establish a spatial gradient in concentration. And whenever you establish a spatial gradient in concentration, that leads to a mass flux. And that mass flux essentially distributes this ink over time, and then if you wait long enough, and you're not studying this ink or anything, if you just wait long enough, then those spatial gradients will disappear. And when spatial gradients disappear, you reach your equilibrium state. All right? So likewise, if I take a container, say, and place it on a hot plate, and the hot plate is at higher temperature than the container. So we know over time, this is how you cook your food, right? Over time, it heats everything up. So there you have an energy gradient or temperature gradient, in fact. So there's a temperature difference, and that temperature difference drives transport of energy. And in this case, the flux is going to be a heat flux. And again, if we wait long enough, we'll establish a thermal equilibrium, and when that is established, the temperatures will be matched. So in chemical equilibrium, chemical potentials would be matched, even though initially we'll be using concentration gradients. You have to remember that chemical potentials are what we really need to worry about, and concentration is often proportional to chemical potential. Likewise, in case of fluid mechanics, we consider transport of momentum, and the way the course is organized is, I've posted the course outline on Canvas, and you can look at that. Initial few weeks would be spent on mass and energy, or heat and mass transfer. Then we'll spend a few weeks on charge transfer, and then half of the quarter is going to be on fluid mechanics. Okay? And we'll try to define each one of these terms in great detail as we go along, but today we'll start with some very elementary relations that most of you who've taken transport phenomena have seen and probably remember very well. All right, so the first idea is defining flux. The second idea is going to be, for all those four cases that we're going to discuss in this class, there are four constitutive relations. And what these constitutive relations allow you to do is correlate each of these fluxes, heat flux, mass flux, charge flux, energy flux, to, in case of heat flux, you have correlation with temperature gradient. And this temperature gradient in the 1D version is something that is probably more easily recognizable as something that's correlated with, say, how temperature varies spatially, right? So the symbol, this delta or inverted delta with a underbar here tells you that this is a vector, and vector means it has both magnitude and direction. So heat transfer is always going to take place in a direction that is determined by the spatial gradients in temperature. And that's something you know very well also from when you sit near a fire, you can determine your orientation with respect to fire and know that this is maximizing your heat transfer. That heat transfer mechanism is something we will not discuss in class because there you rely on radiative heat transfer. Radiative heat transfer is something that also brings solar energy to Earth. This particular heat transfer mechanism actually describes conduction. So this is conduction mechanism, and that requires you to have materials with different temperature in contact with each other, or it could be a same block of material, and on both sides you have two different temperatures. So that first relation that we wrote down here is also called Fourier's law. And if you ever get a chance, you should read his biography. He almost got killed because of his politics, and then he spent a lot of time in Egypt with Napoleon and so on. And that's where he started to get even more interested in heat, right? So Fourier's law, Fourier was actually a very good mathematician. So he not only laid down the Fourier's law, he also came up with techniques to solve heat conduction equations, especially for solids. And then many years later came Fick, who did that we are going to try to emulate throughout the semester. So what Fick realized was that if he had to describe mass transfer, he can borrow all the mathematics from Fourier and have very similar equations. And then if you have similar equations, similar boundary conditions, you'll have similar way of solving this. So throughout this semester or quarter and thereafter, one thing that you should carry forward from these set of lectures is how to learn problem solving for one set of transport phenomena problems, and then just emulate it for everything else that you do in this course and later in life. And so in this case, we will define all the quantities as we go along, but I'm just going to write things where the first important thing we are emphasizing is that there's a flux, and that is related to a gradient. And this one is called Fick's law. Then third one was also familiar to Fick, and in his paper he mentions both of those. And the third one is some version of Ohm's law, which describes a connection between electric current and gradient in potential. So this is current density or charge flux, which means when I say charge flux, then it's clear that it should be charge per unit area per unit time is proportional to electric field gradient. And the one that we'll discuss for second half of this course is going to be momentum flux. And there, when we write the flux term, it turns out that unlike vectors that have 3 terms, it turns out to be a tensor which has 9 terms. And why is it a tensor? What's the meaning of a tensor? Why do we need it? We'll discuss this later. And here again, we have gradients, but these are gradients of velocity, and velocity is a vector, so you end up with 3 terms multiplied with 3 terms, so 9 terms. So all tensors have 9 terms. And so double line represents a tensor. Gradient of a vector is called a dyad. We'll talk about that later. Gradient of a scalar, gradient of a scalar, gradient of a scalar gives you a vector. All right? So in this case, we end up with something that's much older in terms of observations. And those observations were made by Newton, so it's called Newton's law. So here you have heat flux, and that's proportional to temperature gradient. You have mass flux or mass transfer rate, you can call it either of those, and that is proportional to a concentration gradient. And we'll define this later, but this is sort of a mole fraction or mass fraction of A in as, for example, if you had the dye diffusing in a liquid, then that would be mass fraction of A in liquid B. And in case of diffusion or mass transfer, we typically have one species going into another. So this prefactor has DAB, which specifies the fact that you're looking at transport of one material into another. Again, we are just writing these, and later we'll discuss these in great detail. So all these relationships share one common theme, which is they have, in this case, it's going to be energy per unit area per unit time. In this case, it's mass per unit area per unit time. In this case, it's charge per unit area per unit time. And in this case, it's momentum per unit area per unit time. So all of them have the same physical form or definition, and mathematics is very similar. The other thing they all share is that experimentally you can see this. Experimentally you can see this. The greater the temperature difference, greater amount of energy you need to supply to keep or maintain that temperature difference. Greater the concentration difference, greater the mass flux. Greater the potential, greater the current, and so on and so forth. So the proportionality constants in these cases are these parameters that are dependent on the specific material. So K, DAB, kappa, and mu, we are going to define them as material constants or material dependent constants. So K is thermal conductivity. Mu is viscosity. Kappa is electrical conductivity. And DAB is mass diffusivity or diffusion coefficient of A into B, and rho is density, and omega A was your mass fraction. So out of these quantities, all these depend on choice of your material, right? So these are all material dependent parameters, and so what flux tends to show is flux is sort of equivalent to a material dependent coefficient. And we're going relatively slow today, but we'll speed up. And a local gradient in intensive properties. So again, from your thermodynamics, you should remember that intensive means it's independent of mass or size, as opposed to extensive properties that depend on mass and size. Right? So that's what we said so far, and this came about in 1805 or 1806 time frame. This was 50 years later. This was again 19th century. They already understood all this. Newton stated it, but all the vector and tensor stuff probably was filled in again 19th century. So in 19th century they understood fluxes relatively well. But then there was one flux that does not really have this property. It does not have a material dependent coefficient. So there's an exception. And that exception is the electromagnetic flux. Right? So the electromagnetic radiation can travel without need for a material dependent coefficient. And this wasn't something that was easy for people to understand, so they had invented this whole concept of ether that maybe some of you know. So radiation requires no medium. So what we'll do now is try to see what happens if I start with, let's say I start with a slab, a solid slab, and this has some dimension y, and I can define my coordinate axis in Cartesian coordinates as x and y. And initially this thing is at T naught throughout the slab. So T less than 0, you have your solid at T naught. Then at time T equals to 0, we place this slab on a hot plate such that temperature of the hot plate is T1. So this is T equal to 0, temperature of lower plate raised to T1. So now, if we wait for a very short period of time, reasonably short period of time, the heat is getting transferred inwards. But it will take a while before the top gets heated. Right? Of course, it depends on the properties of the material, which are embedded in K, and so on and so forth, but there will be some small time when the temperature profile is going to be a function of both position and time. And then if I wait very, very long, a long period of time, and I have some way of maintaining the temperature at the top at T0, and I have some way of maintaining temperature at a hot plate at T1, which you can do in your home today. If you place something on a hot plate, and T0 would be your room temperature, right? So it's easily accomplished at home. Then you'll find that at large time, you'll get a temperature profile that's independent of time. Okay? So those are the scenarios that happen if I place something on a hot plate. And we'll use this to come back to defining heat flux. So that's one scenario. The other set of problems could be where I again start with maybe, so if I think about textbooks that we'll be referring to, I'll mostly refer to Dean, and then every now and then I'll say BSL, which is Bird Stewart Lightfoot. That's transport phenomena textbook that's used most commonly for chemical engineers, and if you can get access to both of them, it will probably be something you can, those are two textbooks you can keep for life. So when you're in grad schools, one thing you should invest in is at least 2 to 3 textbooks per whatever course you take, and then later you might end up teaching these classes like I'm doing. It becomes real before you know it. So if I take, say, a few silica, and so I have some solid, and I place helium, and I want to look at helium diffusion into it. So right now we're talking about helium diffusion into few silica, but you could equally well talk about soda water bottles and then carbon dioxide escaping from those bottles. So it's again gas in contact with whatever the plastic bottle, and that's a solid. And then what happens here is at T equals to 0, you have the composition of this gas as 0 inside the solid. So there's no helium inside. And then at T equals to 0, we'll do the same thing. We will raise this concentration to some value omega A naught. And one thing that will become clearer as we proceed in the semester is outside concentration might be whatever it is, whatever value it is. The inside concentration, even though it's going to be in equilibrium with it, that equilibrium is in terms of a chemical potential, right? So the concentration of, say, oxygen outside is 20%. When it comes in contact with our skin, there's only a certain amount that can go in, and that amount is determined by thermodynamics and so on. And so this concentration inside is always going to be slightly different from concentration outside. And we'll write this down in terms of boundary condition later. Whereas in case of temperature, you can match them. Concentrations, you need not match them. In many liquid gas systems, you'll probably use Henry's law. Probably say there's some amount of solubility. And that comes from thermodynamics. But in any case, we know the concentration just inside here at T equals to 0 is omega A naught. And on the top, we are able to maintain it at 0 again by maybe having a room where whatever gas comes out on the other side is carried away. So that will maintain the same boundary condition at the top. So again, what happens at small t? At small t, an experiment that you could do easily with a dye. At small time, you'll have some concentration distribution. And that again looks like this profile. And the last thing is, if I wait for a very, very long time, there will be a certain rate at which I need to supply, because I'm losing some gas all the time. So to maintain this assumption that I can get this concentration omega A naught on this side, I have to have that much gas supply. And that could be done if I have a very big container. And then I'm trying to see how that escapes from those walls. Okay, so maybe many of you already recognize this. This is called a steady state. This solution is called unsteady or transient. So now if I think about a chemical engineering, a chemical processing plant, in industry, what you want to do is you might be carrying out a processing, mixing operation, you might be carrying out a reaction. In most cases, you try to maintain the temperature inside your industry or industrial plant artificially using an air conditioner, so you maintain that temperature. And inside, after you wait for long enough, you have a particular temperature, so you usually try to get to the steady state and then just have to maintain the outside and inside temperature. And when you are at that steady state, you'll be requiring a certain amount of energy because you're losing that energy. And that's all you need to know. So in many problems in transport phenomena, we try to get the steady state solution because that's where most of the operation is carried out, or that's where you get to it long enough time. But just like these two examples, I could also write something similar for fluid mechanics. And there's a reason why I'm doing this, because we'll soon solve for this transient profile. And we'll also solve for this profile. Okay? And we can do the mathematics for one of them, and we'll use the same mathematics for all three of them. So if I think about a fluid, so this is fluid between two plates. And at t less than 0, fluid is at rest. Then at t equals to 0, lower plate set in motion. So when I set this lower plate in motion, what it does is it carries fluid with it forward. So this has velocity in this direction. So it has a momentum that is now being transferred to layers of fluid right next to it. And so those layers will start moving. And so if I look at small time, I would see a velocity field which varies with time. So if I wait a little longer, I would get here. If I wait much longer, then I'll have finally, again, this kind of profile, which is V is only function of Y, large T, and that's your steady state program. So if I see all these scenarios, at least, so as far as I'm concerned, there are 3 ways in which most of you will master this subject and any subject. Some of you probably love mathematics, so you look at the equations and you immediately know what's going on. Some of you probably will remember things as soon as they see plots or schematics. And some of you will only enjoy this subject when you read the book, because you need text. And what I'll advise you to do is figure out what's your strength, work with that, and then some of you will be able to use all 3 mechanisms. So if I now go and think about heat transfer, so in heat transfer at steady state, so that's the last figure. A constant rate of heat flow, Q, is needed through the slab, is needed to maintain temperature difference delta T. So you need to keep supplying heat to have that temperature difference. And experimentally, it was found that this heat, rate of heat flow, so it's energy per unit time, divided by area, is proportional to the temperature difference and the distance across this, which this temperature difference is maintained, and the proportionality constant is this K. So that's the thermal conductivity of slab, as we said earlier. And then if we consider a really small slab, a differential element, then we can rewrite everything here as Qy, where what I'm saying in this context is that is just the definition of flux, is equal to minus K dt over dy. Now, why does the minus sign come in? The minus sign comes in because slope always points in direction of increasing temperature, whereas your flux is always from hot to cold object. Right? So that minus sign takes care of that. And that's why we have minus sign here, so that this is consistent with thermodynamics. Again, from higher concentration to lower concentration, which is less precise. More precise is higher chemical potential to lower chemical potential. Again, minus sign. And then we come into this particular thing where if you ever go and give a talk in Wisconsin, then put the minus sign in. If you read BSL, there is minus sign in. If you're not giving talk in Wisconsin, or it's not someone who was taught by Bird, Stewart, or Lightfoot, then you might be able to drop it just like Dean has dropped it. So I have a colleague who is not very happy whenever I use Dean because it's dropping the minus sign. And of course, fundamentally what that means is, in all these cases, minus sign tells you mathematically this points in the direction of increasing values, whereas the flux is in the direction of, from higher concentration to lower concentration, higher temperature to lower temperature, higher velocity to lower velocity. So remember that. So this minus sign, there's a reason for this minus sign, and all other minus signs. So this is what will be called the 1D version of Fourier's law. And in terms of definition or derivation, this is it. It's something that's based on experiments, it's empirical, it's based on observations, it's phenomenological, it's based on phenomena. And from phenomena, people realize that this is a material property and it depends on the choice of material. So it's the same is true for all of these, right? So I can easily then go to a system where maybe this constitutive model won't be followed. So Newtonian fluids correspond to things like water, where this relationship, linear relationship between momentum flux or stress and velocity gradient is true. But in our real life, many of the fluids that we use, ketchup, mayonnaise, shampoos, even blood, all kinds of gels, food materials, paints, drilling mud, all those things don't follow this. So there you need a different constitutive model. Right? So when we look at these things, we later will discuss how this constitutive model assumes isotropic. Isotropic, which means there's going to be the same conduction properties in all directions. That's true for a material that has same properties in all directions. Now if I take a composite, which I can make by taking metal wires, and metal has higher thermal conductivity as well as electrical conductivity, and then embed them in a plastic. So in one direction, the direction of wires, there's probably going to be higher conduction. In any other direction, it's going to be lower conduction. In fact, the specific direction that you're looking at is going to become so important that we'll need to replace this with a tensor and change it. So thankfully, we're not going to do any of that in this class. So it's just for completeness, we'll mention that in some detail later. So this is what happens in one direction. if I have similar quantities in all three directions, then I will get the three-dimensional version of this. And again, when we, after your special vector and scalar recitation on Friday, we'll go back and look at these gradient terms more carefully. But what you'll have is, if you have three-dimensional things, then you have derivative with respect to x and x direction, and this I cap is a unit vector in x direction. In y direction, there's a unit vector in y direction, and in the z direction, and you can have a unit vector in z direction. So this total quantity, instead of writing this expanded thing again and again, all good scientists are lazy. And one way in which they can be saving time and effort is by using terms like gradient, and then you'll see in vectors we'll use the Einstein notation that also simplifies it. So that's the derivation for 1D version of Fourier's law. In my notes, I've included something similar for mass transfer and in a few seconds. And before I finish this discussion, I should say that K varies from 0.01 watts per meter Kelvin in gases to 1000 watt per meter Kelvin in metals or solids. So this tells you that if you wanted to minimize the heat loss, that's where you're figuring out the heat loss, and you started making walls that had more and more gases in them, that is going to be the best insulator. Unfortunately, if you have no walls and just gas around you, it's going to bring in all the cold wave to you. So you do need some amount of walls, but you need to trap air in between. Most of the times when we wear winter clothing, a large part of insulation comes from they're being puffy, because then they trap a fair amount of gas. And again, you can look at their longer problems in BSL that are solved for heat conduction through a composite wall, and I'll mention those as we go on. So likewise, at steady state, the mass flow rate, capital W A Y, because we are again moving everything in that y direction, of helium into positive y direction. Can be described to good approximation by this over area is equal to, or this flux rate is proportional to the concentration gradient, which in this case is this, and the proportionality constant as your diffusion coefficient. For a differential slab, because I'm going to use this diff for difference. So differential slab, which means it's as small as you can make it. You'll have JAY is equal to minus rho DAB d omega A dy dy, and that's your 1D version of Fick's law. And again, we've replaced this by a plus, and you can play the same game in 3 dimension. You can write everything in terms of gradient of a concentration. And the third case we considered in those schematics was steady state laminar flow. Why is it called laminar flow? Well, if you look at it, it appears as if one layer is moving over another layer. They are all moving at different velocity. So they are laminae. So because it's layer by layer, moving layer by layer. So it's called laminar flow. As opposed to what we'll discuss later, turbulent flow that you see maybe when you stand on Chicago, any bridge on Chicago River, you will see the flow is not laminar, it actually is turbulent. So there are lots of eddies and vortices, and that immediately you can see if you have turbulent flow, it mixes things up very well. So we'll talk about that later in semester, but if you have steady state laminar flow, in that case, if I have to move the bottom plate, I have to use certain force, and that force per unit area will determine how fast I can move. So there is a relationship between how fast I can move and the dimension that controls this. And then there is viscosity, which is a material dependent property. So viscosity of water, of gases, is around 10 to the power minus 5 Pascal second. That's a unit. Of water, it's 10 to the power minus 3 Pascal seconds, which can also be written as 1 milli Pascal second. And then if you go to, say, pure glycerol, it can go to almost 1,000 times. I don't remember the exact number, but glycerol or honey or maple syrup could be 100 to 1,000 times water viscosity. So if I have something like air in between my finger and my thumb, and I do this motion, then that's exactly, so I should move on the maybe thumb. So that's exactly this motion. Okay. So the force I need to apply for gas is going to be the lowest. For something like honey or maybe ketchup is going to be much higher, and that you can see from here. So force per unit area is called stress, and you can write this as tau Ix, and we'll say why we use tau and why we use. So keep for BSL. Doesn't matter if you are not following BSL. So what you have here is flow is in x direction, gradient is in y direction. And that's particular property of something we call shear flow. And we call it shear flow because what shear does is if I take a cube and I shear it, then the cube is going to get deformed. If I take these sheets of paper and I apply force on the top surface, then it's going to move the top surface more than the lowermost surface is not even moving. So shear does take something like this, and when you apply force at the top, it's going to move the top surface forward, and so this deformed deformation is going to be delta x, and if this was y, then the amount of shear you applied is delta x over y. And if I take delta x divided by time during which I apply this and divided by y, then if that was shear, this is the rate of shear rate, but this is also same as V over y. So we call this shear rate. And in this case, you have two dimensions because, or you have two subscripts, because this means you are applying force in x direction on a unit area perpendicular to y direction. We'll spend a fair bit of time on defining all the components of stress tensor, and so if it appeals to you right now, it's fine. If it doesn't, we'll talk about it later. But what is important to end with for this is I have now tau yx, and if I divide on the other side with rho and multiply with rho, then you can see something that here we have momentum per unit volume. So this is a gradient in momentum. Is something you can see right away. And then this prefactor is sometimes called nu and has the units, same units as diffusion. So nu and d, the units are meters squared per second. So all these constitutive relationships are empirical. They are defined based on phenomena, and in addition to these four constitutive relations, what we always need to solve transport phenomena problems is a set of principles that are actually more fundamental in nature. So these constitutive relations are all empirical. And they are phenomenological models. So then, apart from using these constitutive relations, we apply four conservation laws with assumption that the fluid can be a liquid or a gas, is a continuum. So the conservation laws are for, again, energy, law of conservation of energy, law of conservation of mass, law of conservation of momentum, law of conservation of charge. So in coming weeks, one of the things we'll do is we'll try to write all these together in a combined form, and then so we'll have a generalized conservation law, and then we'll say that if I have a generalized flux, I have a generalized concentration, how I can use that general one formula to write conservation laws for all of those. That's the first idea. But the conservation law, in some sense, most of transport phenomena allows you to do one thing. So for example, if I wanted to know how soon I'll get rich, then what I need to figure out is how much money I make, how much money I'm spending, and if I have a printing press that's making more money at home. So those are three ideas. How much comes in, how much goes out, and how much you produce. So the rate of accumulation, rate at which you get rich, is going to be determined by how much you make, or how much comes in, how much goes out, and if there is any way in which the money is being produced or being destroyed. It's the same idea that will be applied for each one of those. And we'll write it in any which way. We'll derive it very carefully and write it in all the vector and tensorial forms. But the idea is just this. You're just trying to figure out how much is coming in, how much is going out, and how much is being generated. And how much is coming in and how much is going out, we typically like to think in terms of a volume. And so for that volume, we want to know how much is coming into this volume, and then it makes sense to define everything per unit area, which is why all the fluxes are per unit area. And those ideas should, as we go along, become clearer and clearer. Now, one thing we said here is we are going to assume that fluid is a continuum. So we all know all fluids, gases, solids are made up of molecules. So when you go from one molecule to another, there's going to be a certain distance, and so that means if at a molecular scale they are not continuum. So everything that we do applies only to a certain length scale. For gases, that continuum is 10 times mean free path. And mean free path is an idea that comes from kinetic theory of gases, but all it tells you is that molecules are always, gas molecules are always dancing around. And they can fly to great distances before they encounter another molecule, and those great distances are mean free path. And that mean free path is usually much larger than the size of the molecule. So this distance has to be relatively large. Whereas in liquids, molecules are packed together. That's how you go from gas to liquids. You bring them closer and closer, density is much higher. So in that case, the liquid molecules are also trying to jiggle around, but they can't make jumps that are as large as gases. So in that case, how far they can move about depends not just on their size, but also how they interact with each other. And so those interactions determine what happens in liquids. But in liquids, we can more or less go to almost 10 times the molecular size and say the continuum laws apply. And that is good to know as a starting point, but then of course when you're going to do experiments or simulations, you can check this. But this has been found to be pretty useful in describing thin film dynamics right down to those small length scales. So we are going to try to get to solve for this. Before that, there's one last thing I would say, that all the fluxes we considered, 4 fluxes we defined, were actually examples of what are known to be molecular or diffusive fluxes. And they originate from intermolecular forces and the relative motion of molecules. So for example, in case of fluid mechanics, when I move the lower plate, all the molecules that are right next to it from the liquid are, in fluid mechanics we call it no slip condition. So they're going to be carried away with the same velocity. But as they are being carried away, they'll try to transfer some of this momentum to the next layer and the next layer and the next layer. And that transfer is not very efficient. How far it can be transferred more or less is determined by the property viscosity, which in some sense dissipates this, right? So it's a dissipative form of transport. And how quickly it dissipates things depends on whether you're looking at water or gas or a higher viscosity fluid. So if I wanted to design, say, some way of stopping a fast-moving train, then one way to do it would be to have that train go into a very viscous fluid. But I don't think anyone would like that. So alternatively, you can have the fast-moving parts of the train sort of moving in a fluid, which could be a rheological fluid. And then when you apply a magnetic field, it can go from being liquid-like to solid-like, and that can stop it relatively quickly. Right? So all the fluxes that we considered were molecular and diffusive fluxes. And if I just think about when you get into your car, you switch on heat. Most of the time in winter, what you're going to do is crank up the fan. You crank up the temperature as high as possible, but then you also crank up the fan. And what fan does is it takes the heat from air, a package of heat or a volume of heat, and then it moves it with the flow. So apart from whatever heat can be transferred by conduction, which requires one molecule to transfer it to the next layer of molecules, to the next layer of molecules, and that process can be very slow, you can have some way where everything comes with a bulk fluid. So that second flux, second contribution to flux is convective. And those accompany bulk flow. Again, when you drink your coffee, if you just, and if you drink your coffee with creamer, if you add the creamer and then allow diffusion to do the work, it will take more time for it to mix than to cool down. Whereas what we all recognize already is we have to use bulk flow. So we are relying on convective mixing. And because typically heat transfer and mass transfer are much faster when you have flow, in many practical situations, you need to account for both this transfer and that transfer. And to calculate any convective transport of heat or mass, we really have to then use also for fluid mechanics, because that's what will tell you details about how fast fluid is moving. And then once you know that, we'll calculate how much fluid it's going to bring with it. All right, so the last topic that we'll start today and maybe finish next time is heat and mass diffusion. As I said earlier, the mathematics is quite similar, so whatever we write for heat diffusion will also apply for mass diffusion. And we first will look at problem in solids, or it's also valid for stationary liquids or stagnant fluids. The idea is that I want to first focus on just the molecular flux or the diffusive flux. Right? So we first want to see how fast you can transport heat, say using molecular flux, and we'll derive the equations that we are going to use right now next week. But I'll just write that historically, for solids, Fourier already pointed out that Q is going to be K dt over dx, and then how temperature changes with time. How temperature changes with time is related to where does this equation come from? We'll know, we'll do this next week. But that's a partial differential equation that includes time derivative on this side and includes a spatial derivative on that side. And then there is a coefficient alpha here, which is equal to K, conductivity, thermal conductivity that you've already seen, and this is specific heat from us. So the detailed derivation, when you do it, this rho Cp term goes here, that becomes something that's proportional to enthalpy, and so what you're looking at is how enthalpy is changing over time as determined by how much is coming in and how much is going out. So that's something we'll derive. So this is a partial differential equation that describes heat transfer in solids, which means there's no flow, and we are also ignoring any source terms. Likewise for mass transfer, so this was given by Ian. Decided we could use a similar approach, and now I'm switched to a capital J because we want to define flux in terms of moles, and again next week we'll talk about why we switch between moles and mass. Fluid mechanics people like mass, chemical reaction engineering people like moles, and so if you have reaction diffusion problem, you're often going to use moles. And so concentration in terms of molar concentration, the accumulation really depends on diffusion equation, and that is this equation. So if I want you to figure out my temperature profile or my concentration profile, the unsteady or transient one, I really need to solve this problem. And to solve this problem, I would need, now again, hopefully all of you have had enough ODEs and PDEs, but here what we'll need is initial condition as well as two boundary conditions. And if I look at what we had written down here, we have something for initial condition. Right? For initial condition, we have temperature at the surface. And for boundary conditions, again, we know what happens at this surface and the other surface. So we have all the conditions specified. Then we just need to figure out how to solve this problem. So the way most of the analytical problems or partial differential equations are solved is to try to convert them into ordinary differential equations. And then in BSL, in many books, textbooks, what you can find is sort of a table of most commonly used ordinary differential equations. There may be 10 or 12 of those. So once you master those 10 or 12, you can look at the equation and immediately write the solution. Right? So that's something I hope you'll become very comfortable with by the end of the semester. In terms of analytical solutions to problems, it's a limited set of problems that we can solve analytically. But there is a large number of problems that you can make some assumptions and get an approximate solution to analytical means. And whenever we do get solution to analytical means, those solutions turn out to be very, very useful in sort of verifying whether your computational or numerical solution is correct and guiding your experiment. But more importantly, it allows you to understand what's going on physically. So the problem is to provide steady and unsteady state temperature profile for the case we discussed earlier, so I'm not going to write all that. So before we pursue the solution, what we'll do is your first example of a scaled variable. So instead of using temperature T, we'll rewrite it in this form, where we define temperature as this ratio. So that ratio is dimensionless, but more importantly, what you had in this situation was, the temperatures, two temperatures that you were considering were T1 and T0. Right? So T0 and T1. So you're taking those into account. And you'll see what this does is it makes your temperature, dimensionless temperature, vary between 0 and 1. So it's going to be 0 when T is equal to T0, it's going to be 1 when T is equal to T1. So it goes from 1 to 0 at the top. So those become your two boundary conditions. And my partial differential equation just looks like this. Right, so I'm solving the same problem. The initial condition is when T is less than or equal to 0, your theta is equal to 0. The boundary conditions are when y is equal to 0, y equals to 0, T is equal to T1, so theta is going to be equal to 1. And this is true for all T greater than 0. And likewise, boundary condition 2 is when y. Now, here's the interesting thing. If I look at this problem, my y was actually equal to big Y. So I can solve two types of problems. One problem is where I can say, I'm not interested in figuring out this for a long time. I'm interested in figuring out this at a very early stage. So at a very early stage, we don't care where the other boundary lies. It's far, far away. So in a scenario when we are looking at only small time result, I can assume that there is some distance far, far away where theta is already gone to 0, right? And so this kind of assumption you can make, of course, when we need to define what we mean by short times. And we'll do that very carefully as we move along. But at short times, the slab appears semi-infinite. So you have partial differential equation plus 3 conditions, and those of you who had transport phenomena should just after this write the answer, and those who haven't should go through the long detailed analysis we'll go through. And so I think for all of you we'll go through the long detailed analysis, but what you want to remember here is this is a special scenario in which what we are saying is our length scale to which heat transfer has taken place is much smaller than the overall length scale of the slab. So later we'll also try to look at some kind of scaling analysis, dimensional arguments to get approximate solutions. So approximate solutions are also very useful so that you can get a sense of how temperature is going to vary with time without solving the problem. Okay? So all those we'll learn too. But the first method that we'll use is called the method of combination of variables. Or the method of And the idea is that since your initial condition and boundary condition contain only pure numbers, your solution should be of the form where this theta depends on the only three things that it can depend on. Right? It definitely should depend on space, position, time, and the material property. And the method of combination of variables is a cool method that starts by saying we'll assume that it's possible to write a solution in this way. And this is a hypothesis that you're making, that you can somehow write the solution in terms of a new variable eta. So the idea is that we assume that you can have maybe a solution of this form, where eta is a combined variable or a similarity variable. So let's say this is possible. If this is possible, then this is what you do in your research. You'll say maybe this is what it is, what happens here. If that is true, then we need to verify it. When we start to verify, we essentially go and put this into your partial differential equation, put this into your initial condition, boundary condition. When we do all that, then you have to check if it satisfies all boundary conditions and initial conditions. So it becomes easier to specify and satisfy those if you have these kind of numbers here. And if it works, fine. If an irresolvable contradiction occurs, you need alternatives. You can go solve it numerically on any given day, but every time you have a similarity variable, it's way more elegant. And as you read more and more papers from people in, say, physics department, like Professor Sid Nagel, some beautiful self-similar solutions have come from his group and other groups in UChicago. So every time that's the easiest way to become famous in academic communication. So then you need alternative approach. Otherwise, we are going to assume that our combined variable is of this form, and as we'll solve the problem, we'll find this. Again, this is still a simplified form. I could have written this as x raised to power n p raised to power m form, where we still need to find power law, whether it's what is m and what is n. Later, we'll talk about why we would make this kind of assumption, and if we can see that already from the form of the equation. So that's something we'll learn when we talk about chain analysis. But I think I'm going to end here, because we'll need to, once we start from here, we'll have a fair bit of writing to do. So some of this is discussed in 4.1 in D, and most of the constitutive laws, conservation laws, those are introduced in chapters 1 to 3. So when I teach in UIC, I tell my students that you are all chemical engineers. You should know all this stuff in chapters 1 to 3 from your undergrad. I think here we'll probably try to give you enough background material as well as supplementary material, so whoever has not taken heat and mass transfer before has some way of getting that material. So I will post online my course notes. I teach undergraduate heat and mass transfer, so I'll post those online. They follow BSL very closely, so you can see what I cover there, and you can also read the corresponding sections, and that probably will be useful for everyone to do. And we'll also repeat some of that material in recitation or otherwise. And let me know if you have any questions from maybe next lecture on. We'll try to have office hour right after class, because I teach at UIC and my lab is at UIC, so I'll be coming here only on Tuesday and Thursday afternoons. So.